SR flip-flop works. Okay, SR flip-flop is the one which we are going to learn now. Okay, now this is the gate diagram of the clocked SR flip-flop, where one of the input to the NAND gate is S and R. The other two the inputs of the NAND gates have been shortened, and where the clock pulse will be given to that inputs. So we are working. We are actually learning a positive edge detector circuit which is being given here. So we are learning a clocked SR flip-flop which is positive edge triggered. Okay, so we are learning a positive edge triggered clock pulse which is being given to the SR flip-flop. So this is the block diagram, or you can say the gate diagram for the SR flip-flop. Now case by case we'll see how this SR flip-flop will give the output or give the different states of the output. Okay, so in first case let us assume S and R equals 0. So in first case let us assume S and R is equal to 0. Now this 0 and 0 along with the positive, so let us assume that a clock pulse is been given. So when we give a clock pulse, these two inputs will take an input 1 and 1. Okay, so when we give the clock pulse, these two inputs will take the input as 1 and 1. Now when I NAND 0 with 1, we know the output of the NAND gate will always be 1. So any one input for the NAND gate is 0, then the output of that NAND gate is 1. Similarly, this 0 NANDed with 1 will give 1. Now if we assume Q is 0, then this 0 is given as a second input for this NAND gate 2. This 1 NANDed with 0 will give me 1, and this 1 is given to this one. Therefore 1 NANDed with 1 will again be 0, right? So 1 NANDed with 1 will again be 0. As we all know, NAND gate how it is. So NAND gate is when any one input is 1 or both is 0, both are 0, and if any one input is 0, the NAND gate output will always be 1, right? For this all will be 1, for only 1 1 it will be 0. That is the NAND gate. So therefore this 1 1 makes Q to be 0. So Q was assumed to be 0 in the initial state. Again in the next state you see Q became 0 again. So therefore when S and R is 0 0, if Q is assumed to be 0, you will get Q again as 0. Now let me assume Q as 1. Let me assume Q has 1. So this 1 will come here. So this 1 and 1 is NANDed. So you get 0. Now this 0 is given to this. So 0 NANDed with 1 will give you 1. So in case 1, when S equals R equals 0 0, we saw Qn and Qn plus 1, where Q1 was 0, you got 0, where for 0 0 same, when Qn was 1, you got 1. So it means that this case will say that it is no change. It means when S and R is 0 0, whatever the present state will be there, same present state will repeat again, which is 0. So present state will be equal to the next state when S and R input is 0 0. Coming to case 2. So in case 2, so in let us take in case 2 where S is 0, R is 1. Now this again the clock pulse is given for this. So 0 NANDed with 1 will give you 1, 1 NANDed with 0 will give you 0. So now when we assume q is 0, this 0 is given to this, so 0 will give me 1, and this one is given here, 1 ANDed with 1 will come again 0. So 0 was assumed, 0 came here. So S and R, when it is 0 1, whereas Qn plus 1. So I assumed 0 in the beginning, present state, and I got 0 in the next state also. Now I will assume this as 1. Now I'll assume this as 1. Now this 1 is given to this, so 1 ANDed with 0 is again 1, and this 1 is given to this, 1 ANDed with 1 will give you 0. So therefore, for same 0 1, I assumed Q1 as 1, but I ended up in getting again 0. Okay, so irrespective value of the present state, the next state will always remain to 0. Therefore this is called as reset state. It means that if Qn is 1, it gets reset to 0. Okay, so when you keep S and R to be equal to 0 1 and press the clock pulse, you will see that the output will be 0, even though the present state is 1, but still the output becomes 0. Okay, fine. Now coming to case 3. The next case is, we'll assume S to be 1 and R to be 0, and we have pressed the clock pulse, so this becomes both 1 1. Now 1 ANDed with 1 will give you 0, 0 ANDed with 1 will give you 1. Now let me assume first Q is 0, so this 0 will come here, 1 ANDed with 0 will give you 1, and this 1 is given here, 1 ANDed with 0 will give you 1. See, I have assumed 0, but I end up in getting again 1. I got 1. Okay, so in case 3, S and R, Qn and Qn plus 1 in case 3. So S and R is 1 0, Qn was assumed 0, but I got Qn plus 1 as 1. Now I will assume Q to be 0. Now I assume Q to be equal to 1. Okay, now that 1 will come here, so that 1 will come here, 1 ANDed with 1 I will now be 0, this 0 is given here, 0 ANDed with 0 is again 1. So S and R was 1 0 again, where Qn was 1, Qn plus 1 is also 1. So therefore case 3 can be meant as set state, because when S and R was 1 0, where Qn, irrespective value of Qn, which is a present state, the next state will always remain to be equal to 1. It means when you give S and R equals 1 0 and press the clock pulse, you will see the output remains to be equal to 1 always. So that is the set state. The last state is, the last condition or case is, we will have 1 and 1. So this 1 and 1, after giving the clock pulse, 1 and 1, that makes 0, and this will also be 0. Now assume Q to be equal to 0. This 0 comes here, 0 and 0 ANDed with 0 will give you 1, and this 1 comes here, 1 ANDed with 0 will be equal to 1. So I assumed 0 I got 1. So here S and R is 1 1, Qn and Qn plus 1. I assume 0, I got 1. Let me assume 0 now. Let me assume 1 now. This becomes 1. 1 ANDed with 0 will 1, and this 1 is given here. 1 ANDed with 0 is 1. Therefore, now this need not to be called as a set state, because the set and reset, S stands for set, R stands for reset. So this condition can be possible only when you have S equals 1 and R equals 0. So when S and R both are 1, if you are getting this way of the output, we call it as undefined state. Undefined state. So in an SR flip-flop, in a clocked SR flip-flop, we will see that the inputs when S and R both are 1, it becomes an undefined condition or state. Now this is the truth table of SR flip-flop. When no clock pulse is given, when the clock pulse is not given, irrespective value of S and R inputs, you give any inputs for S and R, if you don't give the clock pulse, the present state what you had will be equal to the next state. Output will not change. Okay, output will not change. So this arrow says you are giving a clock pulse. When you give a clock pulse and Qn is 0, SR is 0 0, the next state will be 0. And we know that when S and R is 0 0, the present state will be equal to the next state. When you give the clock pulse, the present state will be equal to the next state. Coming to S and R 0 1, when you give a clock pulse and when S and R is 0 1, the output gets into reset state. The output will be 0. When you give a clock pulse and if the SR is 1 0, irrespective value of Qn, the output will be in set state. Now when you give a clock pulse and SR is 1 1, the output will be in undefined state. So this is what SR flip-flop is all about. So this you can see a logic diagram. So without a bubble here, there is no bubble here, so we normally call this as positive edge triggered SR flip-flop. So this is a symbol, what you can say is a symbol of SR flip-flop. And this is also a symbol of SR flip-flop, but this is negative edge triggered. A bubble, if you see here, a bubble that says it is a negative edge triggered. So positive edge and negative edge, I told you earlier in the previous video, that is what we are using here to trigger this flip-flop. Now if you look into the timing diagram or the clock diagram of the SR flip-flop, this is positive edge triggered. So till this triggering, irrespective value of S and R, the output remains to be 0. The output remains to be 0. Now when the positive edge triggering will happen, it looks S and R, as S and R both are 0, the output remains to be 0. It means that there is no change. Okay, no change in the output. It remains to be in the same condition until and unless next clock pulse arrives. So at the next positive edge clock pulse, it sees S is 1, R equals 0. So therefore when S equals 1 and R equals 0, it is a set state. It remains to be in set state until the next clock pulse will be arrived. So at the next positive edge clock pulse, S is 0, R is 1. So it is a reset state. Therefore it remains to be in reset state until the next clock pulse is arrived. So this is the clock diagram of positive edge triggered SR flip-flop. Whereas negative edge triggered, this is negative edge. Okay, so the output remains to be 0 irrespective value of SR until the edge triggered clock pulse is given. The output remains to be 0. At the first negative edge triggered clock pulse is arrived, S is 1 and R is 0, therefore it remains to be in set state until the next clock pulse is arrived. This is the negative edge next clock pulse. Now S is 0, R is 0. So when S and R is 0, 0, now S is 0, R is 0. Now when S and R is 0, 0, no change. It was in the set condition, it remains to be in set condition until the next clock pulse. When the next clock pulse is arrived, S is 0, R is 1. So therefore it gets into reset state until the next clock pulse will be arrived. So this is the negative edged SR flip-flop clock diagram. This is how positive edge triggered and negative edge triggered SR flip-flop will work. Okay. Next we'll see the clocked D flip-flop. So let me go to the diagram. Okay. Now why we are using a D flip-flop? See, in SR flip-flop we had two unwanted conditions. See, I need set or reset, but for me no change when both SR and SR is 0, 0 and 1, 1 which is undefined state. With this both conditions I don't need it. I need my flip-flop to give set state or reset state. So for that purpose what we do is we try to connect S and R, we short S and R through a NAND gate. Okay, we try to short S and R through a NAND gate. So now what happens if you short S and R through NAND gate? If I give D equals 0, now S will become 0, R becomes 0, will NAND and it will give 1 as an SR. So if I give 0, R becomes 1. If I give D 0, S becomes 0 and R becomes 1. Now D I can give only two inputs. One input means two combinations, either 0 or 1. So therefore I gave 0, S0 and R1. Now I will have an option of giving one more input which is 1. So when I give D1, then what happens to S and R? S becomes 1 and R becomes 0. S becomes 1 and R becomes. So D was 0, S is 0, R is 1. D1, S is 1, R is 0. So you will be getting only these two conditions in this D flip-flop. So therefore the 0, 0 and 1, 1 conditions are removed, okay, are avoided. So I will be getting only two conditions, either set or reset condition using D flip-flop. So therefore I hope I need not to explain to you, because SR flip-flop is already explained earlier. So when S is 1 and R equals 0, when the clock pulse is given, these both will be 1. So assume Q and see what output do you get. Therefore I will write the truth table for D flip-flop. If you write, this would be the D flip-flop. When D is 0, output is 0. This is reset. When D is 1, output is 1. This is set state. Okay, so that is how the D flip-flop works, and D flip-flop has been designed to avoid 0, 0 and 1, 1 condition that we get in SR flip-flop. So if you see the timing diagram of D flip-flop, this is positive edge triggered and this is negative edge triggered D flip-flop. So here, until the first clock pulse arrives, the output remains to be 0. The output remains to be 0. During the first positive edge triggered clock pulse, D is 1, therefore output will also be 1, and it remains to be 1 until the next clock pulse arrives. So when the next clock pulse arrives, D is 0, therefore it goes to 0. It remains to be 0 until the next clock pulse arrives. At the next clock pulse, D is 1, therefore it remains to be 1 until the next clock pulse. At the next clock pulse, you see D is 0, therefore it remains to be 0. So 1, 1, 0, 0, that is how it is. Coming to the negative edge triggered clock pulse, this is negative edge triggered clock pulse. What you can see at the first negative edge clock pulse, D was 1, therefore D is 1 now. Until that, D will be 0. So D remains to be 1 until the next clock pulse arrives. So next negative clock pulse will see D is 0, therefore it becomes 0 till the next clock pulse. Now the next clock pulse again D is 0, therefore it remains to be 0 again. So this is D flip flop. When D equals 0, output equals 0. When D equals 1, the output equals 1. Now let us learn a very important flip flop, which is a JK flip flop, clocked JK flip flop. Okay. So here this is the block diagram of JK flip flop. What you can see, where an SR flip flop is connected, where S is connected with an AND gate, where one input is J and the R is connected with another AND gate where another input is K. But now the output feedback is given back to the input. So Q is given to K, Q bar is given to J. Therefore that two inputs will make an AND gate output to be equal to S, and this AND gate output will be equal to R. Now let us see how it works. In case 1, when both J and K are 0 0, for example, okay, J and K are 0 0, I can also do here also. Let me explain this only. Okay, so J is 0, K is 0. Initially clock pulse will be given, so at the first positive clock pulse both will become 1 1. Now assume Q equals 0. When I assume Q equals 0, Q is given to this, so this becomes 0. 1 0 0, the NAND gate output will be 1, because any one input is 0, the NAND will give you output 1. Now this is 1, and this 0 is again given to this. So 1 ANDed with 0 is again 1. This 1 is given to this, same 1 is given to this. So this J0 makes S bar to be equal to 1. This 1 ANDed with 1 is again 0. So Q, so JK 0 0, Qn and Qn plus 1. Qn was assumed to be 0, Qn plus 1 is also 0. Similarly now, same JK is 0 0, clock pulse is given. Okay, clock pulse is given. Once the clock pulse is given, now what I should do is I should assume Q to be equal to 0. So I should assume Q to be equal to 0. So this 0 is given to this, and this 0 is given to this also. So 1 0 0 will give you 1, 1 0 will give you 1, and this 1 is given to this and this. Again 1 0 1, the NAND gate output will be 1, and 1 ANDed with 1 will give you 0. Okay. Now if I assume 1 here, if I assume 1, this 1 will give you 1 here, 1 ANDed with 1 will be 0, this 0 is given here, 0 ANDed with 1 will give you again 1. Therefore in JK flip flop, when 0 0 is J and K, Qn is 1, again you got 1, it means Qn equals Qn plus 1. So in JK flip flop, when J equals 0 and K equals 0, then S equals 0, R equals 0, therefore in this output is unchanged state. Okay. Now in case 2, when j equals 1 and k equals 0. When j equals 1 and k equals 0, so here let us put j equals 1 and k equals 0 here. So with this, when the clock pulse is applied, this both will be 1 1, and now if we assume q to be equal to 0, and this 0 is given back to this, and it is given here also, therefore 1 0 0. So any one input of NAND gate is 0, the output of the NAND gate will be equal to 1, and this 1 and 0 is given to this input of this NAND gate, and any one input is 0, again this will be equal to 1, and this 1 is now given to this, and this same one is again given to this flip-flop, this NAND gate. So when all three are ones, the output would be equal to 0 of the NAND gate, and 1 0 will again give 1. Therefore this 0, what was the initial state, has now become 1 again. So in JK flip-flop, if you see, when both 0 0, there is no change. When j is 1 and k is 0, so q n plus 1, what we have, the output would be always equal to 1. The next state will always remain as 1. Now if I assume this as 1, and if we try to see, okay, I'll assume this as 1. Now again same 1 and 0 is what we have. So if I assume this as 1, and I think clock pulse is given, so this both are also 1. So this 1 will make output to come as 1, because this is 0, k is 0. So this 1 whatever we have got, and this 1 whatever we give here, so 1 ANDed with 1 will give you 0. Now this 0 is given back to this, whereas this 0 is given to this also, and this 1 1 0 will make this to be 1. Now 1 ANDed with 0 will again be 1. Therefore qn plus 1 will remain to be in one state when j and k is 1 0. Now in the case 3, where j equals 0 and k equals 1, if I do that, if I try to work on that, so in case 3, if j equals 0 and k equals 1, and if I try to go on that, so let us look into the network again, the diagram again. So we'll try to erase this and say j is 0 and k is 1, and clock pulse is applied. Now what happens here is, when I assume q to be equal to 0, that 0 is given to this, so the output of this NAND gate will be 1. Now the same 0 is given to this, so 0 and 1 ANDed with 1 will give me 1, and that 1 is given here and given here. So because of j equals 0, the output will be equal to 1. Now 1 ANDed with 1 will remain 0. So when j is 0 and k is 1, when q was assumed to be 0, the next state of q is also 0. Now if I assume q to be equal to 1, then that makes this input to become 1. Now this 1 ANDed with 1 will make, this will also be 1 now. So 3 ones, so therefore this will now become 0. 0 ANDed with 1 will be 1. Now that 1 is again given here. Okay, then this 1 is given to this also. So you get one output from this third NAND gate, and 1 and 1 will make the NAND gate output to go back to 0 again. So therefore, when 0 1 is there, Qn plus 1 remains to be 0 always. Whereas 1 1 when I make J and K 1 1, when I make J and K 1 1, and when I give the clock pulse, when I assume Q to be equal to 0, 0 is given here, so 0, you get 1 here for R1, you get 1 here, because 1 input, if it is 0, it is 1. Now this 0 is given to this also, so 1 ANDed with 0 will give you 1, and this 1 is given here, this the same one is given here. So therefore all three ones, so this NAND gate output will be 0, 1 ANDed with 0 will make 1. So when 1 1 was there, I kept Q to be equal to 0, but the next state Qn plus 1 I got 1. Similarly, if I make this as 0, whereas this will also be now I'll make this as 1, so this will become 1, this triple 1 will make this as 0, 0 ANDed with 0 is 1. Now that 1 is given to this, right? Triple 1 is 0, 0 ANDed with 0 is 1, and that 1 is given here, and that same one is given here. So that triple 1 will give 0, this 1 is given, so 0 ANDed with 1 will give you 1 again. Okay, so therefore when J and K are both 1 1, the flip-flop will get into race around condition. Race around condition in the sense the delay between the delay between each state is very less, so that the bit sequences, whatever the next state that it shows as an output, it toggles so fast that you will not be able to see whether the output is 1 or whether the output is 0. So that is what race around condition, it toggles so fast. Okay, so in JK flip-flop, this is the defect what we have when both J and K are 1 1. Okay, so like SR flip-flop, what we saw when S and R are both 1, then we saw that it is an undetermined or not a defined case that we have in SR flip-flop. Similarly in JK flip-flop, when both are 1, we see that you will be getting a toggling condition, and that toggling is what, it's a race around, what we call it as race around condition. Okay, we'll see the race around condition. So now this is the truth table of the JK flip-flop. As you see, when 0 0 is there, it is Qn, whereas when 0 1 is there, the output is 0. When 1 is 1 0 it is there, it is 1. Qn means it is no change. Qn remains to be Qn all in the 0 0. When 1 1 is there, it is Qn bar. For a normal JK flip-flop, it is race around. To avoid race around condition, we create a master slave JK flip-flop. There we see the output properly toggles. It shows each state properly. Okay, fine. This is a normal JK flip-flop which we are discussing. So therefore race around condition is what we see always. This would be the symbol of JK flip-flop, where clock pulse is given J and K. Now this would be the clock diagram of the JK flip-flop. This is the clock pulse, positive edge triggered clock pulse, what you see here. So this is also the diagram shown is positive edge triggered flip-flop symbol. Now if there is a bubble here, then it shows a negative edge triggering flip-flop. So at each positive edge flip-flop, you see that the output gets changed. So therefore here J is 0 and K is 1, so the output gets into reset state. Now at the next positive edge clock trigger pulse, you see both J and K is 1 1, therefore it comes to toggling state, so 0 becomes 1. So at the next positive edge trigger pulse, you see J and K is 0 0, so it remains to be in same condition, because 0 0 means it is no change, so it remains to be in the same condition. When in the next clock pulse, you see J is 1 and K is 0, therefore the output remains to be in the set condition. Now in the next positive edge triggered clock pulse, you see J and K is 1 1. Again it gets into toggling condition and so on. So this is how the JK flip flop works. Okay. So next discussion we'll see what is race around condition, which I just commented with you. Now here you see this waveform clearly explains what is race around condition. So this TP is the time of each clock pulse that we actually give. Okay. So TP would be the duration of each clock pulse that we give, whereas this propagation delay would be the delay between the state that it gets changed. Okay. From present state to next state, the propagation will happen. So the delay, the time taken for that particular propagation is what we call as propagation delay. Now if the propagation delay is made very much greater than TP, then we can see the race around condition can be avoided. So the race around condition in JK flip-flop occurs when both the inputs J and K equals 1. Now if the width of the clock pulse, that is what TP, is too long, state of the flip-flop will keep on changing from 0 to 1 and 1 to 0. See, when the width of this clock pulse is too long, what happens? The flip-flop when J equals K equals 1, the flip-flop keeps on toggling, changing from 0 to 1 or 1 to 0, 0 to 1, 1 to 0, is such that, see, when this clock period width TP is much greater than this propagation delay, then what happens? This toggling condition what we get will run so fast that you will never be able to see what is the change of the state that is been happening here. Okay. So for that reason, you should somehow make the delay, propagation delay, to be much higher than the clock period. If we do that, if the propagation delay has been increased comparatively with respect to the TP, then we can easily say that. So it means that you're trying to increase the delay from 0 to 1 or 1 to 0, whatever the transition is happening, you're trying to increase the time. You're trying to give more delay for that. So therefore, the speed reduces, and you can easily see how the changes that is happening from 0 to 1 or 1 to 0. So you can clearly watch the state properly. That is what that we need, where we can avoid this race around condition. Therefore, that is the condition that we have. So the state of the flip-flop will keep on changing from 0 to 1, 0 to 1, and so on. And at the end of the clock pulse, the output of flip-flop is uncertain due to continuous toggling. This condition is called race around condition. Uncertain means when it changes so fast from 0 to 1, 1 to 0 and all, at the end of the clock pulse, when you see, you will never able to predict what would be the final output of this particular flip-flop, because it's so fast, you cannot predict the output at the end of the clock pulse what it would be there. Therefore, that is what the output of the flip-flop is uncertain at the end of the clock pulse. So this is what the race around condition is all about. So how to overcome with this race around condition? If the time width of the clock pulse is made very less compared to the propagation delay, means if you increase the propagation delay, where the delay or the time taken from each changing from one state to another state, if you increase that propagation delay time greater than the clock pulse width, then we can easily avoid the uncertainty or the race around condition that we come across in JK flip-flop when both J and K equals 1. Okay. So how do we do that? This can be obtained by having a master slave JK flip-flop. Okay, this can be obtained by having a master slave JK flip-flop. So therefore, a master slave JK flip-flop is what we are going to discuss now. So we'll see that now. What is master slave flip-flop? So here in master slave flip-flop, we have a master JK flip-flop and we have slave, which is a normal SR flip-flop. Okay, so this is SR, this is JK. Okay, JK will behave as master, SR will behave as slave. Now, master slave, the word itself says what you can understand. Slave means whatever the master tells, the slave will obey, right? Whatever the master tells, the slave will obey it. So this obeying, this slave behavior in terms of obeying the master's word is what will make the race around condition to get eliminated in JK flip-flop. So how will that happen? Let us see that now. when j equals 1 and k equals 0, master sets on the positive clock, right? So when I have a clock pulse, this is the clock pulse what we have. Okay, when j equals 1 and k equals 0, so j is 1 and k equals 0, this master flip-flop will set, because we know that in jk flip-flop when j1 and k0, q output qn plus 1 is actually always 1. Therefore the master will show its output to be in set condition. So this will make the output y2 go high. Okay, now this high y output of the master drives the s input of the slave, right? This y will definitely drive the s input of the slave. So at negative clock pulse, see, always slave works on the negative clock pulse, because a clock pulse is connected through NOT gate and given to the SR flip-flop. Okay, a complement of the clock pulse is given as an input to the SR flip-flop. Therefore, so at negative flip-flop, slave will set copying the action of master. At negative clock pulse, S will be equal to 1, right? Therefore, this particular slave flip-flop will be under set condition. Therefore, Q becomes 1. Okay, when j equals 0 and k equals 1, when j is 0 and k equals 1, in the same way y will go 0. Now this y will make s to go 0. Okay, and y bar will make r to be equal to 1. Therefore, during positive clock pulse, master will reset. Therefore, during negative clock pulse, the slave will reset. The slave will reset. Okay, so that is one. When j equals 0 and k equals 1, the master resets on the positive clock. The high y bar output of master goes to r of the slave. Therefore, at negative clock pulse, the slave will reset again, copying the action of the master. Therefore, Q will become 0. What happens when both are 1, 1? What happens when j and k both are 1, 1? That is what our job is. So when both j and k are 1, 1, master will start toggling, right? Master will toggle on the positive clock. Then what happens? The slave will then copy the toggling of the master on the negative clock. But the thing is, at this instant feedback input to the master flip-flop are complemented, but as it is negative off of the clock pulse, master flip-flop will be inactive. So at this instant, the feedback inputs what we are given from slave to master flip-flop will be complemented, right? See, at this instant, when we give the feedback to the master from the slave, then the output what we get will be complemented, because it's a toggling condition what we have. But when we give feedback to the master, then during negative clock pulse, what we see is the master will never trigger, right? The master will work only on the positive clock pulse. So therefore, during negative clock pulse, when slave gives its feedback as a complemented bits to the master, then the master will never work because of the negative clock pulse time that master will be facing. Therefore, the flip-flops are complemented, but as it is negative off of the clock pulse, master flip-flop will be inactive. So due to this, what happens? The slave will start waiting. Therefore, for this reason, the propagation delay will increase than the positive than the clock pulse width what we have. Okay, so therefore, in this manner, we try to avoid or prevent the race around condition that we see in JK flip-flop. Okay, so this would be the actual truth table of JK flip-flop. From now, whenever we see JK flip-flop, we come across with master slave only. Okay, we go with master slave JK flip-flop only. Fine. So when 0 0, no change, it remains same. When 0 1, it is 0. When 1 0, it is set condition. For 1 1, now it will toggle, not the race around condition. You will see a proper toggling condition that we come across in the flip-flop when both are 1 1. So this is what the master slave JK flip-flop, whatever we wanted to learn. I hope you people are clear with the master slave JK flip-flop. In my next session, you will see a flip-flop excitation table and how to create this excitation tables of the flip-flop, and then using those excitation table we'll see how to convert from one flip-flop to another flip-flop. Means how to convert JK to D or JK to T or T to JK or D to JK and so on. We'll see how to convert this flip-flop from one form to. Let us learn how the flip-flop excitation tables are written. So for that, the first flip-flop will be what we take is SR flip-flop. Okay, we consider an SR flip-flop. So now the excitation table is been written based on the truth table. Now the benefit of writing excitation table is, further in our counters design and all, we don't go with the truth table of any flip-flops. We normally go with the excitation table of the flip-flops. So it is very mandatory for us to and it's also very important to design excitation table for any flip-flop. And further, with this knowledge of excitation table, we'll see how to design counters, both synchronous and asynchronous counters what we design. Okay, so in SR flip-flop we know that the truth table is what? When both S and R are 0 0, we get the output Qn plus 1 to be equal to Qn. So the next state is Qn. If the present state is Qn, then the next state will remain same, no change. When S and R is 1 0, we see that it is a set state, right? It is a set state. When S and R is 0 1, it is a reset state. Where both S and R 1, it is undefined. It is undefined, right? So with this knowledge of truth table, let us see how to write the excitation table. Now excitation table will always be written with the present state, next state, and the values of S and R. Okay, so this is present state, next state, and how do we get from transition from present to the next state is what the values of S and R will tell. Okay, now if the present state is 0 and the next state is 0, this can happen with two different conditions. Okay, so the present state is 0 and the next state is also 0. So this can happen with no change, and the next state becomes 0 when it is reset state. So no change state is when S and R is 0 0. Reset state is when S and R is 0 1. Therefore S remains to be 0, but R remains to be 0 and 1. Therefore I'll take S as 0, R as don't care. Don't care can take two values 0 and 1. So therefore, but for both 0 0 and 0 1, we see the present state 0 will remain as 0 in the next state. Okay, similarly when present state is 0 and the next state is 1, this can happen only in one single condition, which is set state, is always when S equals 1 and R equals 0. Okay, this can happen with only one single condition of S and R, which is S1 and R0. Then only the next state will remain as 1 if the present state is 0. Therefore that would be the next entry. The third entry is when present state is 1 and next state is 0. So this can again happen with only one condition, where S and R is 0 1. Okay, when S is 0 and R is 1, the reset state will come, which is 0. Okay, the present state is 1 and the next state is 0. This can happen only in one state, when S is 0 and R is 1. Whereas coming to present state is 1 and next state is 1. So this can happen in two different conditions. See, present state is 1, next state is 1. So one condition is no change, the other condition is set. Okay, the other condition is set. So therefore this is happening when S and R is 1 0 and 0 0. For 0 0 it is no change, for 1 0 it is set condition. Therefore now S will remain as X, and whereas R will remain as 0. Therefore it is X and 0. So this would be the excitation table of an SR flip-flop. I hope you have understood how we wrote the excitation table of SR flip-flop. Similarly we write for other flip-flops also. So this is the JK flip-flop truth table and excitation table what we have written. Now in JK flip-flop, truth table is what? When both J and K is 0 0, you see the output is no change. Whereas when J is 0 and K is 1, we see the output would be in reset state. And when J is 1 and K is 0, you see the output is in set state. When both are 1 1, we see the output toggles. So therefore, in JK flip-flop, when I write the excitation table, normally what we write, Qn and Qn plus 1 will be 0, 0, 0, 1, 1, 0, 1, 1. So when Qn is 0, the next state is 0. This can happen in two states. One is no change. The other one is when J and K is 0, 1. So 0, 0, 0, 1. You see Qn will be 0, Qn plus 1 also be 0. Qn is 0, Qn plus 1 is. Therefore, I can say this is 0x for J and K. Qn 0, Qn plus 1 is also 0. Therefore, 0x. Similarly, Qn is 0 and Qn plus 1 is 1. This can come in two states. This is 0, 1. You have 0. See, I have 0 is the present state and I have 1 is the next state. So that can happen when Qn plus 1 becomes 1. And also, that can happen when 0 became 1 is in set state, and 0 becoming 1 in the toggling state. When Qn is 0, Qn bar is 1, right? Therefore, it can happen in two different states. One is when Jk is 1 and 0, and when Jk is 1, 1. So therefore, this can be written as 1x, and that is what you have written, 1x. So similarly, when you go for the next condition, we have the next condition is 1, 0. We do have J is don't care and K is 1. Therefore, this can happen in two states, when 1 and 0, and the Qn is 1 and Qn plus 1 will be 0. That can happen when J is 0 and K is 1, and J is 1 and K is 1. See, 1 becoming 0, this can be toggle state also, and 1 becoming 0 can be a reset state also. So 0, 1, 1, 1, you see that the Qn is 1 becomes 0 in the next state. Therefore, it is x1. Similarly, when both are 1, 1, 1 becoming 1, it can be no change condition, it can be set condition. So set is 1, 0, no change is 0, 0. Therefore, I will write this as x0. Therefore, x0 will come. Okay. So this would be the truth table and the excitation table that we write for JK flip-flop. Now let us look into the excitation table of D flip-flop, how it is been formed. Now we know the truth table of the D flip-flop. The truth table of the D flip-flop is when D equals 0, the next state is 0. When D is 1, the next state is 1. So these are the only two conditions that we see in the D flip-flop. Therefore, if by keeping these conditions of the truth table in mind, we'll try to format the excitation table here. So in an excitation table, you see Qn is 0 and Qn plus 1 is also 0. So if the present state is 0 and the next state is 0, that will happen when D is 0. When D is 0, Qn plus 1 is 0. If the present state is 0 and the next state is 1, that will happen when D equals 1. When D equals 1, though the present state is 0, but the next state will remain as 1 only. Whereas when Qn is 1 and Qn plus 1 is 0, this will happen when D is 0. So even though the Qn is 1, but the next state will become 0 if D is 0. Similarly, if Qn is 1 and Qn plus 1 is 1, this will happen when D is 1. When D is 1, the Qn is 1, the next state will also be 1. So this is the excitation table of the D flip-flop. So now we'll see the excitation table of the T flip-flop. So here in T flip-flop, when T is 0, the next state remains unchanged. Okay, when T is 0, the next state remains unchanged. So if Qn is 0, Qn plus 1 is also 0. If Qn is 1, Qn plus 1 is also 1. That is what happens when T equals 0. Whereas when T is 1, the output will toggle. Okay, the output will toggle. It means if Qn is 0, then Qn plus 1 will become 1. And if Qn is 1, Qn plus 1 will become 0. So therefore, when 0, 0 is there, it means T is 0. Because Qn is 0, the next state is also 0. Therefore, it happens when T equals 0. Now when present state is 0 and the next state is 1, it means it is toggling. Therefore that happens when t equals 1. Similarly, when the present state is 1 and the next state is 0, again this is toggle condition, therefore it happens when t equals 1. Now when both are ones, both present state and next state are ones, this can happen when there is no change, therefore that will happen when t equals 0. So this is the excitation table of the T flip-flop. Okay, so we have covered the excitation table formation of SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. Now using this tables, using this excitation tables, now we will see how to convert one form of flip-flop to the another form of the flip-flop. That is what we will do now. So how to convert the flip-flops from one format to the other format. So what we do here is we convert SR to D, D to SR, and so on. So first thing what we do is we will try to see how to convert an SR flip-flop to D flip-flop. So we will see how to convert an SR flip-flop to D flip-flop. So for this we need to create a table, excitation table for the above conversion. So let us create excitation table for the above conversion. So always if you do any conversion, this would be the way of creating the excitation table for the conversion. Okay, I'll tell you the normal procedure for creating the excitation table for the conversion. You can use the same procedure for even converting any other form of flip-flops to any other form. Okay, so we are doing SR to D, therefore the first column always will be input, and that input would be the flip-flop for which you are going to convert, so that is D. So this column what you put will be the input of the flip-flop which you are going to convert. Then you will have a present state and next state. Then you will put the flip-flop inputs of the flip-flop which you are using to convert, okay, which is SR flip-flop. This would be the columns that we normally use while converting. Okay, now the present state and next state we know we will write 2 bits, therefore 0 0 0 1 1 0 1 1. So this is how we write off the present and next state. Now my job is what? To know the possible inputs of D. D can have only 2, 0 and 1, right? So I will put what happens when 0 0 1 1. Okay, what happens when 0 0 1 1? Now we know in an excitation table, you should go back to the excitation table to write the flip-flop SR. Even D inputs also you should look into the excitation table. For 0 0, D is 0. It means if you go back to the excitation table, see for 0 0 it is 0, for 0 1 it is 1, for 1 0 it is 0, for 1 1 it is 1. So this is what you people need to enter the content here in this excitation table. Okay, so that is how I wrote 0 0 1 1 here. For 0 0 0, for 0 1 it is 0, for 1 0 it is 1, and for 1 1 it is 1. No, this is little bit changed because present state is 0 and No, present state is 1 and next state is 0, then it is 0. Whereas present state 0 and next state is 1, then it is 1. Now it is fine. Now in SR flip-flop, if you see the excitation table which we have formatted earlier, for 0, 0, it is 0x. For 1, 0, it is 0, 1. For 0, 1, it is 1, 0. Whereas for 1, 1, it is x 0. So present state, next state. So this is qn plus 1 in the excitation table. You write the SR content of the excitation table. Similarly, you write for D flip-flop. Now keeping this table, we are going to create a K-map. Okay, so K-map for what? K-map for S and R. K-map for, so when you write the K-map for these two, you will be able to convert the flip-flop to D flip-flop. K-map for S first and then we'll go for R. So while writing the K-map, you are going to consider this D, the input and present state. You don't consider next state for any conversion. You try to take the input of which you are going to convert and the present state. So therefore, then this is a two variable K-map because only two variable D and Qn. So I have D, Qn, 0, 1, 0, 1. Okay, now for S, if you see, this is S. For 0, 0, S is 0. For 0, 0, S is 0. For 0, 1, S is again 0. For 1, 0, S is 1. Whereas finally for 1, 1, S is don't care. Now if I group these two, this K-map, I will be grouping these two. Therefore, I will be ending up in getting S equals Qn gets cancelled, I will be getting only D. So this is for S. Whereas K-map for R. So write the K-map. Again D and Qn, 0, 1, 0, 1. So now 0, 0, yeah, R is don't care. 0, 1, R is 1. 1, 0, R is 0. Whereas 1, 1, R is 0. Now when I group, these two will be grouped. Therefore, this gives me R to be equal to, Qn again gets cancelled, D bar. Therefore, finally, if I write the flip-flop diagram, you will see, first I will write SR flip-flop diagram. So this is the clock pulse, this is S, this is R, this is Q, Q bar, now S is D, R is D bar. Therefore, I will take some input D here, where I connect through NOT gate to R, whereas I connect directly to S. Therefore, this is SR flip-flop. Now, due to this connection, this whole combination will now work as D flip-flop. This is how we convert from one flip-flop to another flip-flop. Now, we will see one more example, how to convert SR to JK flip-flop. How to convert SR to JK flip-flop. as usual we try to write the excitation table of the conversion. So the first thing what we do is we write the JK inputs. So inputs J and K, and then we write present state and next state, present state, next state, and then we write the flip-flop inputs, which is SR flip-flop, S and R. Okay. So this is Qn, Qn plus 1. Okay. Now, as it is a two variable excitation table that we get for both JK and SR, we normally go with 8 conditions. Okay. When Qn is 0, when Qn is 1, when JK is 0, 0, where JK, now when Qn is 0 and Qn is 1, Qn plus 1 is 0, Qn plus 1 is 1. So when do we get this condition? When JK is 0, 0, you get present state Qn, next state Qn plus 1. Again JK is 0, 0. So you are elaborating that excitation table where we wrote the don't care conditions and all, right? So if you elaborate that, you get 8 combinations. So if I go back and look into the JK flip-flop, now this is the JK excitation table which we have written here. So now what I'll do, I'll just tell you how we are elaborating it. So here JK is 0x, 0x. So this can take the value 0, 0 and 0, 1. Similarly here 1x. This can take the value 1, 0 and 1, 1. Similarly x1. This can take the value 0, 1 and 1, 1 again. x0. This can take value 0, 0 and 1, 0. So this is how you get 8 combinations when you try to take out this don't care. Okay, so that is what we are doing here in this particular excitation table while writing. So we are just expanding the JK term. So 0, 0, 0, 0. Similarly 0, 1, 0, 1. If you see, you get all this repeated 0, 0, 0, 0 twice, 0, 1 twice, 1, 0 twice, and meanwhile 1, 1 also twice. Okay, now this will happen when JK is 0, 1, we see present state is 0, next state is also 0. When JK is again 0, 1, we see present state is 1 and next state is 0. When JK is 1, 0, you see present state is 0, next state is 1. And when 1, 0, present state is 1, next state is 1. Whereas for 1, 1, the present state is 0, next state is 1. And for again 1, 1, the present state is 1, next state is 0. So these things happen while seeing the excitation table. Look into the excitation table, and that is how I have written this particular inputs and the present and next state. Now coming to flip-flop inputs, when these are 0, 0, this would have happened when S is 0 and R is X. Whereas 1, 1, present state 1, next state is also 1. This happened when X equals S equals X and R is 0. While looking into the excitation table of SR flip-flop, we are writing this 0x, 0, 1, 1, 0, x0, then 1, 0, then 0, 1. Now what I do, I'll try to write the KMF for this. So now we should take the inputs JK and present state Qn. So it becomes 3 variable K map. So 3 variable K map would be like this. So now input is Jk and Qn present state. So J K Qn 0 1 0 0 0 1 1 1 1 0. So therefore, when all are zeros in the truth table, if you see, so we are writing the K map for S, K map for S, and the K map for R we write. So this is 0. Now for 0 0 1, what you need to do is you need to look here. For 0 0 0, S is 0. For 0 0 1, S is don't care. For 0 1 1, S is 0. For 0 1 0, 0 1 0, S is 0. Similarly, if you write other things, you get 1 don't care 0 1, 1 don't care 0 1. So now which need to be grouped here? So I will group this one and this one. Therefore I will be getting S equals, this 2 will give J, whereas K is eliminated, I get Q bar. So similarly, I'll write the K map for R now. So R is X for 0 0 here, then 0, then X 1 0 0 0 1. Now this will allow me to group these two ones. Therefore R equals J will get eliminated, I get K into Qn. S equals J Q bar, R equals J into K into Qn. Therefore if I write the diagram now, so you will have S and R input, Q and Q bar are the output, and this would be the clock pulse. Now this is Q bar. Now what is S? S equals J into Q bar. So I will take J as an one input, K as an another input. So J into Q bar is S. Therefore I need an AND gate here, where one of the input is J, one of the input is J, whereas the other input is comes from Q bar. Okay, and the output of this is given to S. Similarly, we will use another AND gate for R. One of the input would be K, the other input would be Q. The other input would be Q. Now this will be connected to R. So therefore this is JQ bar, this is KQ. That is what we have written Qn. So Qn, Qn, Qn plus 1, which is Q bar, Qq. Okay, so this is how we convert. Now this complete term will become this complete box, whatever we have mentioned, will now have jk input, q and q bar as the output. This is how we convert SR to jk flip-flop. Now similarly, we can convert any flip-flop to any flip-flop. So last example, I'll just show you how to convert jk to d flip-flop. Okay, let us see how to convert jk to d flip-flop. Okay, now for the first column, the table would be the input of which we are going to convert, d, then present state, q, next state, qn plus 1, then flip-flop inputs, which is now j and k. Okay, so input d will take only 4 combination values, right? One is 0 0, the other one is 1 1. So input d will take only 4 combination values, 0 0 1 1. So when d is 0, then this present state and next state in the excitation table would be 0 0. Again, when d is 0, when present state is 1, the next state is also 0. Now the present state is 0, next state is 1 when d is 1. Present state is 1, next state is also 1 when d is 1. Now if you look into the jk excitation table, we'll see for 0 0 it is 0x, for 1 0 it is x1, for 0 1 it is 1x, whereas for 1 1 it is x0. Now by keeping these terms, we are going to create a k-map and write the k-map for j input and then k input. So when I write the k-map for j, it's a 4 variable k-map, it's a 2 variable k-map, d and qn. Therefore this is d qn 0 1 0 1. So for 0 0 j is 0, for 0 1 j is x, for 1 0 j is 1, for 1 1 j is again x. What I do, I will be grouping these two. Therefore j is now equal to d. Now we'll write the k-map for k. Again 2 variable k-map, d and qn 0 1 0 1. Now when d and qn is 0 0, k is don't care. When d is 0, qn is 1, k is 1. For 1 0 it is don't care. For 1 1 it is 0. Okay. Now the grouping will happen with these two. Therefore k is equal to d bar. So now if I try to write the diagram for this flip-flop, So J, K, Qn, Qn bar, clock pulse, Qn, Qn bar. Therefore now this is D input, J equals D, therefore directly the D input will be given to J. Now for K, a NOT gate will be connected and D bar will be given to K. Therefore this becomes the D flip flop. Okay, J is D and K is D bar, and D is the input. Now this complete whatever the box which I have written will now behave as a D flip flop. So this is how you convert one form of flip flop to any other form of flip flop. Okay, so with this we have learned different excitation table of the flip flops, conversion of flip flops, working condition of flip flops, master slave JK flip flop. We have seen what is race around condition. Okay, so all these things are what we need to know about the flip flops basics. So in my next video we'll see what is the meaning of registers and for what purpose registers are used, and we'll see various different types of registers in my next video.